Okay, so welcome back everybody. At the end of yesterday's lecture, I had written down kind of the what I called the standard form, or what's called linear normal form for, or maybe I should just first say, what is a linear equation? Just to remind you, a linear equation is one that can be brought into this form. Most general possible linear equation looks something like this. So you would have p of t dy dt plus q of t y is equal to r of t, right? This is like the most general possible linear equation. Of course, in some of the ways that I wrote this down yesterday, I had everything on the left-hand side, so the right-hand side was 0. But here I have the thing that doesn't depend on y or derivative of y is on the right. This is just a convention. This is a very useful convention that we'll talk about, or that especially will be stressed in the second third of the course. But this is a nice way of writing this. Now, if I want this to be 1, the thing multiplying dy dt to be 1, I can divide through by p of t and rewrite this thing as dy dt plus q of t over p of t y is equal to r of t over p of t. All right. Now you might say, wait, this p of t function can be 0 somewhere, right? Like, what if I have something like this, right? So what if my example is like t dy dt plus log t y is equal to like t squared, right? So this is a linear equation. If I divide through by t, I have dy dt plus log t over ty is equal to t squared divided by t is just t. Right, so I would get this thing. Okay, this is a linear equation, but I've divided through by this t, and now I've introduced some. Whereas it didn't seem maybe immediately like this had an issue. Of course, this is log t, so it already had an issue at 0. But you can see how if this wasn't log t, if this was just 1, right? Dividing through by t, now I've introduced an issue here where at t equals 0, this is now a function that is undefined. We'll talk a little bit more about that later. So in what's talked about in section 4 in the notes. So chapter 1, section 4, we'll talk a little bit more about this. Right now we're kind of just dealing formally with this, but yes, of course, you could end up, when you divide through by this p of t, wherever p has zeros, technically you have introduced an issue here, but we're going to see that you already had an issue in the first place, because wherever p is 0, this term gets zeroed out, and near those points, or especially at those points, this equation is now not really a differential equation. It's like just some kind of weird algebraic equation, right? Doesn't involve derivatives. And we're going to see how we're going to toss out those points anyway. So whether we divide through them by not, it's actually not going to matter. Those are going to be problem points to us regardless. So anyway, we'll talk a little bit more about that later. So anyway, I'm going to relabel this as I did yesterday. I'm going to relabel that a of t and relabel this f of t. Okay, so that a linear equation is one that can be brought into this form. So dy dt plus a of t y is equal to f of t. This is known as linear normal form. And everything going forward in studying linear equations is going to assume that whatever equation you're dealing with has already been brought into this form. Okay, so of course, the typical problem may be to solve this equation or the IVP, right, where this is some initial value. Again, doesn't have to be 0. This is t sub I. This is how the textbook or the notes labels it is equal to some initial value, y sub I. Okay, this is the IVP in question that we're solving. So a linear equation can be brought into this form. If you can't bring the equation into this form, then it's not linear. All right, it's a nonlinear equation. So this is first order linear equation. This is what they look like. Okay. So the first third of the course is going to be studying first order equations. So chapter 1 deals only with first order equations. First order equations are simple, or at least simpler than higher order equations, just because, think about it, right? Even in the case of linear equations, like this is, you can only have 3 terms here, right? The more derivatives of y you allow, even for a linear equation, you're going to get more terms because you would be allowed to have a second derivative term and a third derivative term and so on. And of course, for a nonlinear equation, this really gets complicated for higher order stuff. It's already going to be complicated for nonlinear equations, even for first order stuff. But chapter 1 deals only with first order equations, so we're talking about first order linear equations here. We won't get to second order and higher linear equations until chapter 2 stuff. That's the middle third of the course. Okay. So we saw an example of this yesterday when we did our kind of guessing, right? So our example was this. So we had something here. I'm going to write it like this. So from yesterday, we had this example, dy dt minus 3y is equal to 0. You might say, wait, we didn't quite have that example, right? Well, we saw it in a different form. It was dy dt is equal to 3y. That was the form we saw it in. And we saw that the solution to this, we arrived at by kind of thinking, oh, well, what's this saying? This is saying I have an unknown function y. When I take its derivative, it's 3 times itself. It's 3 times the function I started with. So we saw that the general solution was c e to the 3t, right? That was the thing that did it. Okay. Now, just to introduce some notation that we're going to use throughout the course, when you have a linear equation like this, okay, we can see here that a of t is the constant function minus 3, and f of t is the constant function 0. So both a and f are 0. Okay. When the right-hand side function is 0, this is called a homogeneous equation. And it's homogeneous because of this 0 on the right. So compare this, if you've had Math 240, then this was also the same terminology used whenever you had the matrix equation AX equals 0. Right, that was a homogeneous equation. So a homogeneous equation means if you've put it in this form, the right-hand side function is 0. Okay, that's not going to be typical. Typically, we're going to have a right-hand side function that's just some function of t. But in this special case, where this is 0, this is particularly nice. You get something like this. Okay. So the point though is how do I deal with something maybe a little more complicated here, right? So how do I deal with something that's maybe just slightly more complicated? How about something like this? Let's say, actually I'm going to write it like this. So dy dt is t squared y. Is this linear? Is this a linear equation? Remember, don't get caught up in the fact that this is a t squared here showing up. That's not important for linearity. What's important for linearity is that it can be put in this form. All right, well, can it? Yeah, if I rewrite this as dy dt minus t squared y equals 0, this is, again, a homogeneous equation. It's linear. It's dy dt plus function of t times y is equal to some function of t, which in this case is just 0. Okay. All right. And how would I solve this? Well, again, I kind of guess here, right? I kind of guess. I say, okay, well, now I'm no longer in the case that I take derivative of unknown function and what I get is constant times the function itself. I get t squared times the function itself. But I kind of use the same idea here, and I make a guess. And my guess is, well, like, I kind of want to use the same idea here, where this is going to be like constant times e to the something that when I take its derivative, I get t squared. So that would be e to the 1/3 t cubed. Let's check that this works, right? So again, as I said yesterday, the great thing about this course is every single problem is going to have you finding solution to differential equation. And if you want to know if you're right, you can just check directly that this thing actually verifies the differential, or this thing actually satisfies the differential equation. So here I take dy dt. What's dy dt? dy dt is 3 times 1/3 t. So this is going to be the derivative of this thing, which is 3 times 1/3 t squared times c e to the 1/3 t cubed. 3 times 1/3 t squared is just t squared. And c e to the 1/3 t cubed is y. So dy dt is t squared y, which is exactly what it needed to satisfy. Okay. All right. Now, clearly, this process is not always going to work, right? This, in fact, only worked us using and abusing the fact that we know exactly how the chain rule works, and we know that e to the whatever, right, satisfies. So if I have, I'll write it like this. Really, both of these solutions are us abusing the fact that we know that if I have e to the, I'm going to call it big A of t, and I take the derivative of this, right, then what I get here is big A prime e to the big AT, right? And so, if I am in this situation where I have dy dt plus a of ty is equal to 0, right, then really I'm in the situation dy dt is equal to minus a of ty. Right, and so in this case, I can abuse the fact that I know chain rule here to say let this little a be related to big A by somehow saying something like I want big A of t to be a function such that big A prime of t is like minus little a, or I'm going to write it like this, even though you might notice that the sign is wrong if I write it like this, but I'm going to write it like this for now, right? This was our idea. Okay, essentially. But of course, if I have a little a that is related to this big A in this way, then really big A is just what? It's just the antiderivative of little a, right? Okay, so that's really what we're using here. Now, let's do a quick. Here, I'm going to do another example. Let's do. Okay. So here's our equation. I put this in linear normal form. If I can, I divide through by t squared. So this is dy dt plus y squared is equal to log t over t squared. But then you notice, oh, right, like there's a problem here. This term, that's not allowed. Having a y squared there is not allowed. All right, so this is not linear. And there's nothing for me to do with this thing. Some of these equations that are nonlinear we will have a way to deal with, but sometimes you're just stuck. Okay, so can't do anything with this one. Alright. Now, how does this, what's my idea here for how to go forward when I don't have a homogeneous equation like this? So let's say that instead I have a completely general linear equation that looks like this. What do I do here? So, in general, I'm not going to go through every single derivation in this course. A lot of times I'll just kind of spoil the fun and immediately move to the last bit that kind of shows how everything works. The idea is to use something called an integrating factor to rewrite this as an explicit differential equation. So the idea is to use what's called an integrating factor to rewrite this as an explicit. Explicit means this is dy dt is equal to blah, some function of t. So it's to rewrite this as an explicit differential equation. What is this integrating factor? So first step, as above where we had this idea here, let big A of t be such that the derivative of big A of t is equal to little a of t. This just means that big A is the antiderivative of little a, right? i.e., big A of t is the integral of little a of t dt, in the sense that it's the antiderivative of that thing. Okay. Okay, so let's do that. Suppose y satisfies dy dt plus little a of ty is equal to f of t. Right? And when I mean it satisfies this, it means it satisfies it for all t. Now, for right now, we're not too worried about where this differential equation is satisfied. We're just going to say everywhere. What will actually turn out to be the case is that for a given differential equation, there's what's called an interval of definition. And this interval of definition you can think of as like the largest interval on which this differential equation is satisfied by some function. So when I talk about having a solution, I'll talk about having a solution on some interval of definition. We'll talk about that in the subsection 4. Right now we're kind of doing things a little bit more formally where we're not that worried about where these things are defined. So suppose y satisfies dy dt plus a of ty is equal to f of t, and we'll say, like I said, that it satisfies it everywhere. Okay. All right. So then what I want to do is notice that if I take the derivative of this thing, what do I get? Well, let's use the product rule here. Right? Let's use the product rule. So using the product rule here, I would have ddt of e to the big A of t times y plus e to the big A of t times dy dt. Okay. All right. Well, what is the derivative of e to the big A of t? Using chain rule, right, this is big A prime of t, e to the big A of t, y, plus e to the big A of t, dy dt. But we've said to let big A be such that big A prime is equal to little a. So then this is really little a. And I'm going to rewrite this. So I'm going to rewrite this as e to the big A of t dy dt. So I've swapped the order of this so you can see what's going on up here. So e to the big A of t dy dt plus little a of t e to the big A of t y. Well, what is this? Well, this is just the left-hand side of this equation, except I've multiplied it by e to the big A of t. If I multiply the left-hand side by e to the big A of t, I have to multiply the right-hand side by e to the big A of t. And so e to the big A of t times this, which is what I have here, since y satisfies this equation everywhere, what is this? This is just e to the big A of t times f of t. So rewriting this, the derivative of e to the big A of t times y is equal to e to the big A of t times f of t. This is called the integrating factor form of the equation. The integrating factor in question is this e to the big A of t. That's my integrating factor. Okay. All right. Now, why is this nice? So why is this nice? Because it is explicit in the sense that what I have is derivative of something is equal to some function of t. Notice the very important thing here is on the right hand side now all I have is a function of t. There's no y showing up. So I have d dt e to the big A of ty is equal to e to the big A of t f of t When you have an explicit differential equation, what was the way we talked about to solve this? Well, I just integrate. So I integrate both sides. And so what this tells me is that e to the big A of ty is equal to the integral of e to the big A of t times f of t dt. I'm going to go ahead and add in a constant of integration that arises from this integral. I'll call it big C. Okay. Now I divide through by e to the big A of t, and what this tells me is that y of t is equal to e to the minus big A of t times the integral of e to the A of t f of t dt plus c times e to the minus big A of t. That is my solution. So this is my recipe for first order linear solutions. Now you can either memorize the integrating factor form of the equation. A lot of times that's what's suggested because this is simpler, this is a shorter thing to remember. Or you can simply memorize this last step here. In either case, you have to know that this big A of t is such that big A prime is equal to little a. And so what this means is that big A of t is really the integral of little a of t. And so it is true that this is just the closed form recipe for any solution to a linear first order equation. But one thing to know here is that to actually write this out, you need to do two integrals. Okay, so this involves two integrals. So what are the two integrals? The first one is this integral. Okay, or well, maybe that's not the first, that doesn't make sense to call that the first one because really the first one is this one. So the first integral that you have to do in order to even write this thing is this one. Okay, so the integral of little a. And then the second one is this one, the integral of e to the big A f of t dt. Okay. Notice if we go back to our, so note, if we go back to our example, let's do dy dt is equal to 3y. If I write this in linear normal form, this is dy dt minus 3y is equal to 0. So a, or little a of t, is equal to minus 3. F of t is equal to 0, as we said. Well, if little a of t is equal to minus 3, then big A of t, which is the integral of a of t dt, is minus 3 t, right? You might say, wait, this is an integral of a of t, so this is the integral of minus 3, so this should be minus 3t plus c. That plus c is taken care of by the other integrating factor, so you don't have to worry about it here. Okay, so you can just write this as minus 3t. Okay, so here's my big A of t. This is minus, so big A of t is minus 3t here. And so if I write out y of t from this recipe, the first thing I get is the e to the minus big A of t times integral of e to the big A of t f of t, but f of t is 0, so this is just going to be the integral of 0. This is just going to be 0. So I'm going to get 0 plus c times e to the minus big A of t, i.e. y of t is equal to c e to the 3t. So this recipe, of course, worked in that first example we did. We did it in a different way. We did it kind of intuitively, just thinking about what that differential equation said for our unknown function y, but this shows that this applies to that example we did just as well. Okay. All right, so let's do this for maybe something a little bit more involved. So find a general solution to the equation dy dt is equal to minus 3y plus e to the 2t. Okay. So I'm going to use this recipe. So first of all, it's definitely linear. Let's put it into linear normal form. This would be dy dt plus 3y is equal to e to the 2t. There's my linear normal form. All right, once it's in this form, I can identify the pieces here. So a of t is the constant function 3. F of t is the function e to the 2t. Okay. So big A of t is the integral of a of t dt. So this is the integral of 3 dt. This is just 3t. Okay. So let's go to our recipe here. The general solution should be in this form. All right, so then general solution should be in the form y of t is e to the minus big A of t times the integral of e to the big A of t times f of t dt plus c times e to the minus big A of t. Okay. So then this is going to be e to the minus 3t times the integral. A lot of times, of course, if this is more complicated, you would want to do this integral separately and then just write this in one step. You wouldn't want to waste your time writing all this notation down, but I'm just going to do it this way. So then e to the big A of t is e to the 3t times f of t. F of t is e to the 2t dt plus c e to the minus 3t. Okay. So e to the 3t, e to the 2t, that's e to the 5t. So this is e to the minus 3t times the integral of e to the 5t dt plus c e to the minus 3t. And what's the integral of e to the 5t? This is 1/5 e to the 5t. So this is e to the minus 3t times 1/5 e to the 5t. You might say, where's the plus c? The plus c has already been accounted for here. Plus c e to the minus 3t. And so what is this? Ultimately, this is 1/5 times e to the 2t plus c e to the minus 3t. All right. Now, the question becomes, is this actually the solution to this equation? Well, let's check it. All right, so let's check it. This is not something, you don't have to check every single one of these. This is purely us doing this just to make sure we understand what's going on and to make sure the thing we found is actually a solution. So let's check this thing. So let y of t be equal to 1/5 e to the 2t plus c e to the minus 3t. Let's take the derivative of this thing. So what is dy dt? So dy dt is equal to 2/5 e to the 2t minus 3c e to the minus 3t. Right? Okay. So and to do that right, I think I did. I think we're all right now. And now this y should satisfy the equation dy dt plus 3y is equal to e to the 2t. So let's make sure that it does. So what is dy dt plus 3y? Well, that is equal to, so dy dt is 2/5 e to the 2t minus 3c e to the minus 3t plus 3 times y, which is 1/5 e to the 2t plus c e to the minus 3t. That's just directly from here. So minus 3c e to the minus 3t plus 3c e to the minus 3t. Those cancel. What I'm left with is 2/5 e to the 2t plus 3/5 e to the 2t, which is 5/5 or 1 e to the 2t. But dy dt plus 3y is equal to e to the 2t. That's exactly the differential equation that I claimed I was solving. All right, so that is exactly what I wanted it to be. And indeed, this works, right? So our general solution is this. Okay. So let me know if you have questions about that. Okay, let's do more examples. So let's do something. So here's another example. So find a general solution to the equation 1 plus t squared dz dt plus 4tz is equal to 1 over 1 plus t squared squared. Okay. So here the unknown function is labeled as z instead of y. Right? That's not an issue. A lot of times it'll be x. A lot of times it'll be z or some other thing. Okay, so here it is. What do I do? Well, the idea here is the same as before. The first step is to put this thing into linear normal form. So let's do that. So let's put this into linear normal form. What is this in linear normal form? Well, if I divide through by 1 plus t squared here, what I get is dz dt plus 4t over 1 plus t squared times z is equal to 1 over 1 plus t squared. Instead of squared, this is cubed now. Right? So here is the differential equation in question. Notice we have no hope of being able to solve this by guessing, right? Even the previous one, right? Even the previous one was something that, looking at this equation, you would not have just in your head kind of come up with this expression to make this work. All right, so once you're dealing with non-homogeneous equations, even for first order thing, this guessing method is just not going to work. Clearly, you're not going to be able to look at that. Okay, I'm looking for an unknown function such that when I take its derivative and add 3 times the function to itself, I get e to the 2t, right? That's not going to tell you too much. So here, even more so, right? You're going to have almost no idea what the final form of this thing is going to look like. All right, but let's say here we go. Now, once we've written it in this form, I identify, my little a of t is 4t over 1 plus t squared, and my little f is 1 over 1 plus t squared cubed. Okay. So let's compute the things I need. So what do I need here? Well, I need, first of all, to compute big A of t. So this is the integral of little a, which is the integral of 4t over 1 plus t squared dt. Hmm. So let's think. I'm going to use u sub here. U is going to be 1 plus t squared. Then du is 2t. I don't have 2t here. I have 4t. So I have an extra 2. So this is going to be 2 times the... Maybe I'll just rewrite it like this. All right, so this is 2 times 2t over 1 plus t squared dt. And through u sub, you can see that this is just 1 over u du. So this is 2 times log of 1 plus t squared. Okay. Now you may have noticed in this course, depending on the courses you've taken before and the instructors you had, maybe they already started doing this. But from now on, for the rest of time, in a math course, when you see log of something, this is the natural log. Okay, so this is ln. The reason we use log is there's no other log for us. Any other log is stupid and pointless. You know that there's the logarithm change of base formula anyway, so you can always use whatever base logarithm you want to. So why not use the best one by far, objectively? So natural log, and that's that. So every time you see log showing up, that's what's meant, is the natural log. So this is 2 log 1 plus t squared is going to be our big A of t. Okay, so then now I have my recipe, right? So what does my recipe tell me? So then my recipe gives me the following. So z of t here is going to be given by, and I'm just going to rewrite the whole thing. So this is e to the minus big A of t times the integral of e to the a of t, f of t, dt, plus c times e to the minus big A of t. Well, remember that here our A of t is 2 log 1 plus t squared. So e to the minus big A of t in this case is going to be e to the minus 2 log 1 plus t squared. We use log rules here, so this is e to the log of 1 plus t squared to the minus 2. So really this is 1 over 1 plus t squared to the 2. Right? So that's what e to the minus a is. E to the a is this thing squared. Right? So what is this? This is going to be equal to 1 over 1 plus t squared squared times the integral of e to the big A of t is, well, it's the reciprocal of this. So it's 1 plus t squared squared times f of t. Let's remind ourselves, what was f of t here? F of t was 1 over 1 plus t squared cubed. So this is times 1 over 1 plus t squared cubed dt plus c times e to the minus a of t, which is 1 over 1 plus t squared squared. Right, so this is what I get. Let's simplify that a little bit. So this is 1 over 1 plus t squared squared times the integral of these cancel. What I'm left with is a single power of that in the denominator. So this is 1 over 1 plus t squared dt plus c over 1 plus t squared squared. What is that integral? Someone can tell me, maybe. What is that? while I write this. This is 1 over 1 plus t squared. Squared times, what is that? This is arctan. This is arctan t plus c over 1 plus t squared squared. And there it is. So you may not have guessed, right, when you originally glanced at this differential equation that the solution of that would involve an arctan, but in fact it does. All right, or maybe you would have guessed that, right? Maybe you'd have looked at that and said, okay, it's reasonable to think an arctan might show up. All right, there's the original equation I started out with. Here was the equation in linear normal form. All right, and here is the general solution of that equation. Okay, I'm not going to check it for this one, but you could if you really wanted to. You could check that when you took the derivative of z and added to that 4t over 1 plus t squared times z, you would get 1 over 1 plus t squared cubed. Okay, so you could actually check that if you really wanted to. All right, so notice that in all cases, our ability to write out solution came down to being able to compute those two integrals. Now, in a completely general equation, you're not going to be able to compute those two integrals. But in this course, we're going to very nicely deal with problems where you do, right? Like where you're able to. So what I want to do now is to go back and do examples involving IVPs. All right, as I said, IVPs are equations like this, for instance. So consider the IVP that is dy dt is equal to minus 3y plus e to the 2t. And let y of 0 be equal to 2. Okay. Now you hopefully look at that and say, wait, we've done this already, right? In fact, this is our first non-homogeneous example. This is exactly what we solved here. Here was our equation. We already found that the solution to this was the following, right? The general solution was this thing. So we already have a general solution that we found using our recipe. Our general solution is y of t is 1/5 e to the 2t. Lost connection really quickly. Let me know if I'm back. Things are buffering and jumping around. Okay, so maybe when you watch this, there was, a brief period, maybe 15 seconds of buffering and jumping around, skipping. So I don't think I said anything too important there. Okay. Okay, good. That's good to know. Okay, so the general solution then, like I said, is parameterized by a family of constants, or rather it's parameterized by this constant c, which can take on any real value you like. So it's an infinite family of solutions. This IVP could be thought of as once you specify an initial value, you have selected out one of those things. Okay, so you can view, we're going to talk about this a little bit later. If I were to plot this for different values of c, this is exactly the sort of thing you're going to do in MATLAB, by the way, right? This is the thing that computers are great at. If you wanted to plot like 10 of these, right, for 10 different values of c, you could do that and see how they fill out the plane. This hints at a few things that are going on, okay? And I'll mention that when we get to the section 4 stuff, talking about existence and uniqueness. That's a very important part of this. Anyway, so here is our general form of solution. Here is the initial condition, as we saw yesterday. To actually find the solution to this IVP, I impose this initial condition on this general solution. So 2 is equal to y of 0, which is 1/5 e to the 0 plus c e to the 0. So this is 1/5 plus c. So then c is equal to 2 minus 1/5. Well, 2 is 10/5, so this is 9/5. Okay, and so the unique solution. So I'm going to underline unique right now, and I'm not going to say why that I know that this is unique. We'll talk about that later, but it's unique in the sense that this is the only one. There's no other one that solves this IVP. The unique solution to the IVP above is y of t is 1/5 e to the 2t plus 9/5 e to the minus 3t. Okay. So notice that for an IVP, you first kind of ignore the initial condition, right? You ignore the initial condition first. Solve this in the way, by the recipe in this case. So there's our solution that we found. And then you impose the initial condition to select one of those from the infinite family out, and this is the one that has been picked out. Okay. So that's how that works. Let's do another example. Actually, before I move on, the textbook actually, or the notes, do a good job of showing what it is that's going on. If I were to plot like a few of these, right, what would the picture look like? So the picture would look something like this for different values of c. So maybe one value of c looks like that. Here's another. Here's another. Here's another. And here's one more. And this particular value is selected out of those, right? Maybe it's like this one. Maybe I like circle that one. And that's what has been picked out here. Now, something that you'll notice if you were to, say, like I said, grab MATLAB or whatever your favorite computing environment is for doing this sort of thing, and have MATLAB plot a few of these, right? Or have Wolfram Alpha plot like a few of these for a few different values of C. If you plot it on the same plot, you'll notice that, oh wait, like they look kind of the same. They have like a similar shape, but they don't cross or touch. They get very close, and sometimes it looks like they converge to certain behavior, but they don't touch nor do they cross. And that's an important thing later, as we'll see, and that is the thing that tells us that these solutions to IVPs are unique. Because if they did touch, if they did cross, we could select that point where they touched or crossed as our new initial point, our initial condition, and then emanating from that point, we would have two different possibilities. We'll see that that's impossible, right? It's not really obvious a priori why that would be impossible, but we'll see that that's going to be impossible. Okay. All right, let's do one more example. So our other linear equation that we did. So solve the IVP, which is 1 plus t squared dz dt plus 4 tz is equal to 1 over 1 plus t squared squared, with initial condition z of 1 is equal to pi. Okay. So we already found the general solution to this thing. The general solution was z of t is arctan of t over 1 plus t squared squared plus c over 1 plus t squared squared. Okay. Imposing the initial condition in the same way, pi is equal to z of 1. Z of 1 here is arctan of 1 over 1 plus 1 squared squared plus c over 1 plus 1 squared squared. So then what is arctan of 1? Let's think for a second, right? So arctan of 1, I'm looking for where tan is 1. That's where sine and cosine are equal. That's where, what, this is pi over 4, right? So this is pi over 4. So this is pi over 4 over 1 plus 1 is 2. 2 squared is 4. Plus c over 4. Right, so pi is equal to pi over 16 plus c over 4. So let's see here. I need to, if I subtract, so if I subtract, I think pi over 16 from, so if I subtract pi over 16 from pi, I get 15 pi over 16. Right, is equal to c over 4. So then multiplying by 4, I get that c is 15 pi over 4. Yeah. And so what is my solution to the IVP? It's this. I've just replaced c with 15 pi over 4. So maybe I'll do it that way rather than rewriting this. All right, there's my unique solution to the IVP. All right. Okay. So that is how this process works. Now, again, once you've seen the recipe, right, it's just a matter of applying it. And what does applying the recipe mean? Well, applying the recipe here means basically being able to do this two integrals. So let's review a little bit. So once you know the recipe for a linear equation, so a first order linear equation, it is simply a matter of applying it. I.e., computing two integrals. So the two integrals in question are this one, the one that computes big A, and this one. Now, as I said, for completely general functions, like if I just let little a of t and little f of t be whatever functions I want, the hope, the probability that you'd be able to compute these integrals is 0. Because in general, if you just write down the nastiest function you can think of course, that thing is not going to have an explicit integral typically. But in this course, we are going to select problems specifically that allow these integrals to be computed in a nice closed form, really nice way. But this is what you have to do. So what are the kind of the three components for solving a first order linear equation? You have to know the recipe, and then you have to be able to do this integral and this integral. If you know the recipe, doing these two integrals, you're going to be able to just write out the general solution from that. Okay, so that is how this goes. All right. So there's not too much more to do here. Now you may ask me like some kind of logistics questions, like what kind of integrals do you have to know in this course? Generally, we don't give you too like hard trig sub integrals, anything like that. But you do have to know all the basic integral stuff, all the basic integrals, of course. So, you should know the arctan integral that we just did. You should definitely know substitution. Got to know substitution. Got to know the basic integrals, like, obviously, like all the polynomials, 1 over t. You got to know e to the t, cosine, sine. Got to know substitution. You should know integration by parts as well. So all of those are required. No trig sub stuff. We'll eventually get to you needing to do partial fractions, which in the context we do them in won't even have to do with integrals, really. But if you include that in integration knowledge, then you have to know that eventually. And that's all I can think of right now. But you'll get a feel for it when we're doing more and more of these things. Okay. So that is that for first order linear equations. You know the recipe. How to apply it is simply a matter of doing the integrals that show up. Okay. So then next I wanted to talk about the next class of first order equations, separable first order equations. So these have a different form. So the form that these take is the following. All right, dy dt is equal to f of t and g of y. This is one of the reasons why we suppress the notation. So remember, y, this unknown function, is actually a function of t. So technically, right, if we wanted to, everywhere y shows up, we could write parentheses and a t in there. We don't do that because, one, that would be really annoying and redundant. Like, once I tell you y is a function of t, I don't have to keep reminding you by putting the parentheses and the t in it. But also, it serves a practical purpose of allowing us to say exactly this thing that intuitively is kind of obvious, but if we had these t's floating around everywhere, it wouldn't be as obvious. The idea here is that we can separate the variables t and y. Now you might say, wait, y is not a variable, y is an unknown function. True, but I'm going to pretend, for the purposes of what kind of equation this is, I'm going to pretend that both t and y are variables, right? So just t and y are letters showing up in these equations. And if I can separate them out like this, so that f is a function of t only, g is a function of y only, and dy dt is equal to f of t g of y, this is called a separable first order equation. So again, separable here means that these things can be separated into this product. Now, not every equation is separable. Okay. Lots of examples of where these things cannot be separated. So we'll see plenty of such examples. But maybe, it's kind of... The textbook uses a subcase of this called autonomous equations. I won't refer to autonomous equations till a little bit later in the chapter because there's not too much reason to. We're going to see how we're going to go about solving this, but maybe first let's do a few examples of separable equations here. So, for instance, What kind of equation is that? Well, this is linear. First order equation, of course. It's linear, but also separable. How to see that this is separable? Move this to the other side. So dy dt is equal to sine t times y. Oh, there's my f of t, and there's my g of y, right? So in this case, f of t is sine t, and in this case, g of y is just y. Okay, let's do another example. So, okay. So here's my equation. Dy dt plus y cubed minus y squared is equal to y plus 57. What kind of equation is that? This is not linear. All right, so this is a nonlinear equation. Is it separable? Well, let's try to put it into a separable form. This is dy dt is equal to minus y cubed plus y squared plus y plus 57. I claim that this is equal to f of t times g of y. Well, I claim that g of y is minus y cubed plus y squared plus y plus 57. And f of t is 1. Right? Then yeah, this is equal to f times g in that case, right? So either of these, either f of t or g of y, can actually just be constant. Specifically, they could just be the constant 1. Okay, so for instance, explicit differential equations are examples of separable. Those are the ones where g of y is equal to 1. And what are called autonomous first order equations, which is when f of t is equal to 1, are also examples of separable equations. We'll talk a little bit more about autonomous equations later in section 5 of chapter 1. Okay, so this is separable. Okay, this is separable. All right. Let's do another example. What kind of equation is this? Well, this is linear, right? It's already in linear normal form, so this is linear. Is it separable? Well, let's try to separate these things. So I get dy dt is equal to minus t squared y plus log t. Can I separate this out? No, right? Now, if this log t was a t squared, could I separate this out? Yes, I could. I could factor out a t squared, now we get t squared times minus y plus 1, and that thing would be separable, okay? So sometimes a non-homogeneous linear equation can be separable, but in this case, it's not. I can't separate this out. This is not separable. So we've seen a bunch of different cases here, right, where we had linear and also separable. So it was both linear and separable. Non-linear, but separable. And linear, but not separable. So any of those are possible. Okay, separable equations, because they include nonlinear equations, tend to be nastier, tend to exhibit more complicated, complex behavior than linear equations. Of course, sometimes separable equations are linear, right? So there's that. But typically, separable equations, especially the nonlinear ones, are a lot more nasty, a lot more complicated. So we're going to see some examples of that. But anyway, this is just to give you kind of a little list of examples showing what is and isn't separable. Returning to our separable equation here, what is the idea? So this is a common thing that we did, in calculus, was to, this is kind of the great thing about Leibniz notation here, right? So Leibniz's notation, dy dt, this is just notation for the derivative, of course. This is not actually a fraction. But you've probably already seen examples of where treating this like a fraction is actually really nice, because intuitively it kind of tells you exactly what it is that's going on here. So I'm going to abuse the fact that, or I'm going to abuse the notation a little bit, treat this like an honest-to-God fraction, and I'm going to separate, since they can be separated in this manner, I'm going to separate further by putting all of my expression that depends on y on one side and all my expression that depends on t on the other side. So I'm going to clear denominators here, right, by multiplying both sides by dt and dividing both sides by g of y. What I get is the following. So I get 1 over g of y times dy is equal to f of t times dt. This is known as separated form. Now, why is this nice? This suggests what we should try to do next. What we should try to do next is integrate both of those, right? You have functions times dy, function times dt, function times d something, where the something is the variable the function depends on. That suggests you want to take an integral. This is what we're going to do. So just like for linear equations, our solution to this is going to rely on us computing two integrals. Okay. Anyway, but unlike linear equations, we're going to have one more step, okay, which is where a lot of the nastiness comes in. So anyway, we'll do this tomorrow. So I think that's it for today. So I will see you all tomorrow, same time.